So there you go. So we were doing equilibrium last Friday, right? And we'll do a bit of 3D equilibrium. And as I was saying, 3D is a little different. We're doing point equilibrium. We're not getting into full equilibrium yet. We'll do that later. So if we're just looking at the equilibrium of a point, like a little object without any significant dimensions, we got 3 equations and 3 unknowns. We got our 3 force equations, x, y, and z. So in this 3D stuff, I take a more formal approach. First thing I want to do is break everything into Cartesian vectors. Cartesian means x, y, and z. Now, if you got unknown forces, you find the unit direction vectors and multiply them up by the unknown magnitudes, which is fine. You can do that. And then we'll build a matrix. There are 3 rows, x, y, and z. The forces are put in columns, is how that works. And then solve out the equations. All right? So that's how we do that. So on 250, you ought to have something that looks like that. So let's say we've got a sphere that's held up by these 3 wires, OA, OB, and OC. And the sphere weighs 9,000 newtons, plus we got the force of the wind on there. Let's find the force in each of the wires and express our answer as scalars and vectors. Okay. And then we got some, little notes here like we do. OA is in the negative x direction. OB runs along the x-axis. Excuse me, I just misspoke, didn't I? OA is in the negative y direction. OB runs in the x-axis. And then the angles there reference the force of the wind. So why don't you come up with the wind force as an x, y, z vector, a Cartesian vector. Okay, that wind force ought to be something on the order of 1650, 5720, and negative 731 or thereabouts. You all get into that okay? So you just take the magnitude of the force, the 6,000 times the cosine of the 3 angles. I mean, that's how you do that, right? We okay with that? Doing all right? Any questions on that bit? All right, now if we're good now the other three of the others are the weight, FA and FB, and they're all pretty straightforward. The weight x down and the negative z. FA is shown there in the negative y direction. That's called out in the notes down below the sketch. And then FB goes right along the x-axis. Now notice FA and FB have unknowns in the vector, and that's fine. Just don't know what the magnitude, but you know some other things about it, so you want to be able to write that vector up as shown there, okay? So there's a start on getting those forces, you might say vectorized. I don't know, that's not really a word, but we could make it into one. Okay. So any questions on any of those things? You doing all right? All right, now we've got the other one is OC, okay? Now we don't know what the magnitude of that force is, but we got the dimensions to it. Of course, it starts at the origin. Of course, I put the origin there at the center of the sphere. So the origin is there, like so. And then it extends out to that coordinate location there. So why don't you find a unit vector going from O to C, okay? So what's the unit vector going from O to C? And, take these opportunities to get good at this stuff and, to figure it out and knock through it pretty quickly. When we have our exam and all that, you're just going to want to knock this stuff out, eh? So have a look and get that unit vector, okay? If you got questions, ask somebody. Okay, so we want a unit vector from O to C. So start off with the vector from O to C, which ought to be pretty straight up, and then just do the whole unit vector stuff. Now we'd like to make that into a force vector. Of course, we don't have a numerical magnitude to multiply through by, so we'll have to use an unknown magnitude, which would just be FOC. But you want to start off with that unit vector. Doing all right, minus, oops, that's a highlighter. So minus 2, 1, 6, is that the coordinate there? All right with that, and you just do the whole unit vector business, because you're starting from 0 on this one, so you don't really need to do any subtraction. if you were doing subtraction, it would be kind of trivial to do it, but you'd have negative 216 for point C. So that would, and then you'd have minus your beginning point. So what I'm doing here is just to kind of make this a more general process. There's ROC, and then we'd have RO, and of course that's just 0, 0, 0, okay? So, you don't need to do the subtraction step on here that you need to do with most of the vectors. And actually, I didn't label that properly. That should be RC. There you go. So what this will get you then is ROC, okay? Now, this is a little bit silly to do this, but, this is the normal process when you've got one coordinate on the beginning and the other on the end that you would use, okay? But being as you're starting at the origin, it's not really necessary to do that, okay? Okay. So that gets you RO, and then you want to what? Find the magnitude, and then you want to divide through by the magnitude and get the unit. You all good with that? And I'm kind of talking about you for the test here. Just, when you do these tests, it's not like you got time to be kind of figuring out what to do. You want to be spending more of your time doing it, okay? That's kind of why I'm saying this to you. So this is one thing you want to know how to do it. Step, 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 bang. Then get on with your life on to the next one, okay? All right. Good. So something like that, 6.4 for the length, which is the magnitude, divide through by that, and then scale it up by the force magnitude, which is just FOC. See, we don't know what that is yet, so that just factors through the unit vector. It's unknown right now. Now we're going to figure out what it is, but we don't know yet, okay? So just leave it as an unknown, factor it through. Just like you'd multiply through by, if that force happened to be whatever, 2,000, you'd multiply 2,000 by each of the components. We're doing the same thing here. And let's see. Yeah, I used a notation there that I'm not real happy with. I sometimes see this after the fact. I really ought to have, if using the form I'm using, I really ought to throw an I, a J, and a K in there is what I ought to do. It almost looks like we're just adding them up like a dot product or something. We're not. It's I, J, and K. Okay, so I should have used a little bit better form on that. Okay. All right. So there's the unit vector, and again, I don't know what that is. So I'm just gonna, excuse me, that's the force vector there. I'm just taking that unknown FOC and multiplying it through the unit vector is what I'm doing. Okay. All right, so now I've got everything vectorized. I've got I think it's 5 of those forces expressed as Cartesian vectors. Cartesian meaning they have X, Y, and Z components. So what I'm going to do now, I'm going to put them in columns in a matrix. And then the rows are going to be X, Y, and Z. That's my next step. And when I build this matrix, what I've got are 3 equations, see? One for the X, one for the Y, and one for the Z, and they're just good to go, and I can solve them now and find my unknowns. So that's why I'm doing this, okay? So I'm going to take everything and just drop them into columns like that, right there on the top. So this is step 2. So I got FA, FB, FOC, F wind, and F weight, and they're just in columns, see? And normally I'll put the unknowns on the left side and the forces on the known forces on the right. Algebraically, I just like that a little better, okay? All right. So y'all okay with this? I'm making a matrix out of it is what I'm doing. And I've got FA, FB, FOC, F wind, and F weight. They're columns, they each got 3 terms. Remember to put the zeros in there. And then the rows then are the X, Y, and Z components. Now the blue stuff, which I guess I'll underline just for fun. So the stuff that's blue, so that's that and that and that. I'm just underlining this. The reason I'm doing this is it's occurred to me that in a class of 40, there might be people who don't distinguish blue from green very well, so maybe might be 1 or 2 people. So the stuff I'm underlining, that's just the forces just dropped in columns. Now the stuff in green, which I didn't underline, is I'm taking those rows and I'm turning them into equations. And that's easy enough to do. I just put plus signs between the terms and set it equal to 0, because I know it's equilibrium. So I know the sum of the x's is 0, the sum of the y's is 0, sum of the z's is 0. That's equilibrium, okay? Okay. So I'm just taking that matrix and I'm putting the appropriate signs in there, plus signs to add everything up, and then setting them equal to 0, and that gets me 3 equations and 3 unknowns. So that's step 2, build a matrix. Columns are forces, rows are x, y, and z. So we good with that idea there? And then the last step is to solve the matrix. Now again, if you've got a solver on your calculator, I guess you could solve out is that a 3x5 matrix? But you could also work through this one algebraically. Right. So what I'm going to do to solve that thing algebraically is I'm going to look for a row that has only one unknown, and I find it, that's z. So using the z row, I can solve for FOC, it's 10,385. That's the magnitude of the force in that wire that goes from O to C. It's 10,385 newtons, I assume there, yeah, newtons, okay? Now I can take that and plug it in for all 3 FOCs, all right? So once I found that magnitude, I can plug it in for all 3 of those, okay? And so now FOC is a known after I do sum of FC, so then I can do sum of FY and solve for FA, that's 7343, and then I can go sum of FX and solve for FB, and now I've got all 3 magnitudes of the 3 wires. Okay, so 10,385 and 7,343 and 1589. A little bit of rounding difference, you know, depending on how you do it, but that's what you come up with. Doing all right with that stuff? Now we got the magnitudes, okay? There's a little spot down at the bottom, I think, to fill those in. Okay, now in the past I've had people ask me, you know, on a test, do we have to solve out a matrix? And the answer to that is probably on a test I wouldn't do that. Probably, see, I don't want to have you spend time on the test showing me a lot of math skills. You know, you got to master math and know how to use it, but on a test, I'm testing you for statics, not for math, okay? So a matrix would take a while to solve it out. I probably wouldn't do that on a test just because I don't want you to burn 10 minutes solving a matrix, you know. You can do that in a math test, but I'd get you something more straightforward you could knock through algebraically like you're seeing here, okay? All right. So we okay with that? All right. Now, the last thing we might want to do is get those unknowns expressed as vectors. See, notice there's no vector arrows on top of those numbers there for OC, A, and B, or FOC, FA, and FB. They're just magnitudes, you know, they're just newtons is what they are. So if there's anything on there, it ought to just be newtons, you know. So if we want to turn those into vectors, what we would do is we would just multiply those numbers now through the unit vectors. You know, the first two are pretty trivial. FOA is just 0, negative 73430, and FOB is 158900. FOC, you just have to now take the known magnitude, which is 10,385, multiply it through the unit vector, and that will get you the three actual components of force, as shown there, okay? Everybody all right with that little bit there? Just factor the magnitudes through the factor the unit vectors for the unknowns. That's all we're doing there. So lots of calculations on these, you know, and I just want to keep nagging you about just slow, systematic, you know, take your time, don't drop negatives because they just blow everything up when you do, okay? So just develop those good habits. When I was working, I spent a full week, 40 hours, designing a road transition about the size of this room here. Went from a crown section to an inverted section, and it had a little angular jog in it. And I spent all this time just calculating all these grades and making sure it drained properly and all this crazy stuff. You know, it took me a long time. So, you know, so any mistake I made on Monday would have showed up on Friday, and that would have been a bit of a mess. So, you know, just take your time, nice and slow. You know, at this point, you're probably thinking, oh, this homework problem's pretty bad. But man, you start working on actual things are really going to get complicated. I don't know if you ever seen a set of plans for like a water treatment plant. There's just pipes going every which way on them things, and you know, someone's got to keep track of all that stuff. So, you know, just get those habits down. Slow, systematic. It saves time in the long run. I was working for a small company at that time. So Friday afternoon, one guy leans over my shoulder and told me I was using the wrong base map. They hadn't kept them straight, so I was a little unhappy about that. So I was working off the wrong set of coordinates and map to begin with for all these detailed calculations. So I didn't say anything. I just stood up and left and walked around a little bit. I was pretty good. Anyway, we got it. It got built. It's fine. It works. So we're good. Okay. All right. So we good with that? We got any questions? Okay. Okay, we're good. Okay, how about 253? You two can do three-dimensional statics equilibrium problems. So let's have a look at this one. Why don't you get, let me start with F1. That's probably where I started. So why don't you get F1 as a vector, just vectorize that, okay? Again, that one starts at the origin, which means you can skip a step that you normally have to do. Doing all right? Yeah, if you got questions, just ask me, or ask your neighbor, or ask somebody. difference of the endpoints to get the vector, square root of sum of the squares to get the length of the vector, and then divide it out to get the unit vector. And scale it up by the magnitude. That's the drill on that. So the length of that thing ought to be 7, just as a check, we can work it out. And we get that unit vector. The magnitude of the position vector.
For Cartesian vectors, should we write the unit after the whole vector or after each component inside the vector?
The what now? The Cartesian?
For Cartesian vectors, like you write at like 5 newtons, comma 7 newtons, comma 3 newtons, or you write 5 comma.
I put it.
Okay.
And I don't always include the units when I'm going through. It's a little, a little tedious and messy, but yeah, I put the units at the end.
Okay.
I put everything in brackets.
So why?
Okay, y'all getting to that? 2 minus 3, 6. Get the square root of 49 for 7 and divide through by that. And then scale it up by 4,000. Y'all doing okay with that? Questions on that stuff? Everybody getting that all right? So 1143, negative 1714, 3429. Good? Okay. All right. Okay, let's have a look at that next one then. How about F2? Why don't you come up with a unit vector for F2? Now pay attention to those dashed lines. Everybody just kind of have a look at that and figure that one out, okay? The dashed lines are kind of the key to that, to getting that one, getting the right angles in there for the unit vector for F2. Okay? We went through one of those a while back. I just want to be sure one can kind of visualize that and work through it. So we want a unit vector for F2.
Well, you have to multiply.
So you want to find those three angles is what you want to do to get that unit vector. Okay, we're doing all right with those? What do we got for alpha?
27?
Yeah, 27, I would hope there, okay? So that's the easy one. All right, now what we got here with those dashed lines, they're the key to understanding this or visualizing it or whatever you want to say there. What we're doing here is we're coming off the z-axis in the x direction, aren't we? Because we've got this dashed line is parallel to the x-axis. And then we've got the other dashed line is coming down from the x-axis. like so, and that's parallel to the z-axis. So we're coming down from the x and the z direction, and we're coming over from the z and the x direction. So it looks to me like that vector F2 is in the xc plane. Okay, that's the key to this. You don't really need both of those lines. One would suffice. Okay, because like if you use the one over here, you're coming down from the x and the z direction. That tells you that it's in the SC plane. But 2 is a little nicer. You can kind of see it, and it helps you visualize a little better. Okay, all right. So we're in the XZ plane. Okay. Now once we're in the XZ plane, what's the angle then with the y-axis? It's 90, right? And it doesn't matter where you are in the XC plane. So if you've got a wall that's the XC plane, the y-axis is normal to the wall, right? So any vector in the XC plane is normal to the y-axis. Okay, it's just that simple. It doesn't matter where the vector is in the XC plane. It is normal to the y-axis. So you can draw a line anywhere on the wall you want, which would be that vector. And it's always normal to a line normal to the wall, which is the y-axis. It doesn't matter, okay? So as long as F2 is in the XC plane, it makes a 90-degree angle with the y-axis. What's the cosine of 90? 0, right? Because it doesn't have a y component. It's in the XC plane. There's no y component, so that unit vector piece will 0 out. That's the deal, okay? All right. And then gamma. Okay, now what's up here is we know the angle between x and y is 90, right? We also know that this angle's in the xz plane, as is that angle. If two angles are what I call coplanar, you can add them because they're both going in the same plane. You can arithmetically add them. That's a legal thing to do, so to speak. Okay, so you can take 27 and 90 and add them up and get 117. Okay. Now, if angles are not coplanar, you can't add them. But if they are, you can. Okay.
You can also just take minus the sign of that 27.
You can, yeah. There's a lot of things you could do with this one, right? You could from a teaching perspective, so I can come up with a nice simple phrase. I say find the angle with the positive axis and take the cosine of it. Yeah, but you're right. You could take negative sine 27. You also could take negative cosine 63 if you wanted to. There's many ways to get that figured out, okay? But I'll just stick with cosine of 117 because I can explain it easily and it's systematic and it's simple. But there's other ways to do it, sure thing. Okay? So if you want to find that vector F2, what you're going to do is you're going to take the unknown magnitude times the cosine of the angles here. So cosine 27, cosine 90, and cosine 117. Okay, so that's the vector F2. Okay, so you've got F1, F2, you got F3, and F4. So you just want to make vectors out of all 4 of those, put them in a matrix and solve it. That's how you do that, okay? You shouldn't need to use a solver on this one. It's a pretty straightforward matrix to work through, okay? Good with that? All right. Okay, so that's a bit on 3D equilibrium there. And I'll have you finish this page you're on. Now keep in mind, it's not problem 253, it's page 253. And then I'll get you another one of these to do. That was a little bit of practice at these, so let's see what we got here. Do we need practice? copy of the notes. Is there like a number 182 or something for homework? Maybe there is. I'm not sure. Yeah, 182. So page 253 and then problem 182. Okay? And these will be due Wednesday also. We'll go over these tomorrow. So Wednesday is the 11th, I think. All right. Now we got a couple minutes, so I want to start something new, but that's the 3D equilibrium. So the 2D equilibrium is more, the way I do it, I just kind of look at it and figure out the trigonometry. The 3D, I get more systematic. Make Cartesian vectors out of all the vectors, put them in columns in a matrix, and solve out the rows. Is how that goes, okay? All right. So that's how we, so we good with any of that? Good? All that, I should say.
So which problems and all are due on Wednesday?
It's a good question. So 253 and 182, those for sure do. And then I think there was 171 and 173, I think.
Yep.
And then there's probably at least a couple before that. Oh, that's good.
171, 173.
So there's 4?
Yeah.
Oh, that's good. Okay, good enough. So 171, 173, page 253, and then problem number 182. So just 4. Okay. Okay, now I did enter all your homework scores for the first one in Moodle. So, you might check and just have a look at it, be sure it's there. But it should be in there now.
Problem 182, the one that we just did.
That was page 253 that we did. 182 looks a lot like it, but yeah, page 253 is the one we started. And then 182 is another problem that we haven't worked on at all yet.
So not the one with the 3 cables either.
What's that?
So it's not the one with the 3 cables?
No, that was a different page. That was page 250. So 182 it's got cables on it. I don't know. It looks a lot like these. It's similar in how it's set up. Should be, yeah, it's pretty similar to how these look. It's the same sort of problem, but it's just different numbers. And I'll go over those tomorrow. All right, why don't we just look at something here quick, and then because we only got a couple minutes, but if we're good with that. But, let's see, do I want this? I guess I do. Now, what we've been dealing with so far are just little points, finding forces and different things that act on a particular little point. What we're going to do next here is look at objects that actually have dimension, okay? And what we're going to look at is something called a moment, which is a twisting action. Okay, so, well, that's interesting. What do we got there? Okay, we're good. All right, so what we got going on here is we've got a green motor on the top that outputs a torque. That shaft is being spun with a certain amount of moment, twisting action. And what that's going to do is turn, I believe that's a pump down below in blue, okay? So this is called a moment. It's a twisting action. Okay, so a moment is a twist or a torque about an axis. And I shouldn't say and, it should say and. Oops, come on. No, never mind. Oh boy. Okay, so that's about an axis there. So if you twist the lid off a jar, you're creating a moment about the center of the lid. Now, if you're having trouble twisting the lid off the jar, what you might do is put a little bit of a wrench on there and apply a force with your hand. And that's another way to generate a moment. Have a force and an offset distance. Okay. If you're ever using a wrench, you're exerting a moment about the nut or the bolt or whatever it is you're turning. Okay. So it's force times distance. Okay. So if you want to increase the moment, there's two common ways to do it. The first is to get angry and just pull harder, right? And that generates more moment, okay? But there's a smarter way, isn't there? Okay. And as you probably know, the smarter way, so first is to increase the force, and you can do that, but the smart way is to increase the distance. And back when I did more work on my car, I had what's called a cheater bar, a pipe, galvanized iron pipe about 3 feet long, and I could usually either get the nuts off or twist them off. Just twist the bolt and break it. I could do one or the other with that thing. So that was pretty good. Okay, so that's the basic idea of a moment. Okay.
I thought the moment was how hard it was to turn something, and the torque was how much I can't remember, or how much of an effect you were getting in turning something.
Mm-hmm. I tend to use the terms interchangeably. They're all indicate a twisting type action. I'm not, there are certainly a lot of words for it, torsion, torque, moment.
Yeah. I thought that torque was the equivalent of force, and moment was the equivalent of inertia.
Yeah, I'm not aware of any real finer definitions of those terms. I just use them all interchangeably, so I don't know. Okay, so that's what we're going to get into next, is looking at objects that have dimension and causing these twisting actions around objects, okay? So we'll do that on Wednesday. Well, we'll probably start it tomorrow. We'll go over the homework first tomorrow, then when we're done, we'll get more into this. Okay?